Did you know there's water on the moon, not just in shadowy craters but in regions bathed in sunlight? Imagine standing on the moon's surface, sunlight blazing down on a vast crater, only to discover something that could change the future of human colonization. Scientists have uncovered a truth that challenges everything we thought we knew. Stay tuned to find out more about this astonishing breakthrough and its implications for humanity. For years, our understanding of lunar water was straightforward. Any water on the moon must be locked away in permanent shadows. These are the frigid, sunless craters near the poles, where temperatures plunge to minus 250 degrees Fahrenheit, cold enough to trap and preserve water ice for billions of years. Scientists thought the relentless sunlight elsewhere would vaporize any hint of moisture, rendering the rest of the moonbone dry. That was the belief, until recent missions rewrote the narrative. Enter NASA's SOFIA, the Stratospheric Observatory for Infrared Astronomy, a telescope mounted on a Boeing 747. Flying high above Earth's atmosphere, SOFIA had a clear view of the moon, and what it found stunned the scientific community. It detected water molecules in Clavius Crater, one of the moon's largest craters in the southern hemisphere, and crucially, in a sunlit region. How could this be? Scientists quickly realized they needed to rethink their assumptions. It turns out that water on the moon might be shielded from the sun's harsh radiation by microscopic grains of lunar soil. These grains, acting like tiny umbrellas, create pockets where water molecules can persist without being instantly obliterated by sunlight. Does this mean that the moon is wetter than we've ever imagined? Could these sunlit reservoirs be the key to sustaining life and building infrastructure for future missions? This discovery raises a tantalizing possibility. If water exists in places we thought impossible, what else might we find as we push the boundaries of lunar exploration? In the next section, we'll dive into how this discovery reshapes our plans for living, working, and exploring the moon. But first, can you imagine what it would be like to tap into a water source on another world? Let us know your thoughts in the comments below. Imagine finding water where it's least expected, right under the sun's glare, in a place as harsh and desolate as the moon. The idea seems as implausible as stumbling upon an oasis in the middle of a scorching desert. Yet, in these sunlit craters, water is defying the odds, quietly surviving in one of the most hostile environments known to humankind. So what makes these craters so special? To understand this, we first need to contrast them with the moon's shadowed craters. Shadowed regions, especially those near the poles, are places where sunlight never reaches. Temperatures there remain eternally frigid, providing a natural freezer that traps and preserves water ice for billions of years. Sunlit craters, on the other hand, seem like the exact opposite. These areas are exposed to the relentless heat of the sun during the lunar day, with surface temperatures soaring to over 260 degrees Fahrenheit. At first glance, such conditions appear utterly inhospitable for water. However, these sunlit regions have their own unique properties that enable water to exist. For one, the lunar soil in these craters is a master of adaptation. Tiny grains of regolith, the fine, dusty soil covering the moon, act as protective shields for water molecules. These grains can trap water within their structure, insulating it from the harsh solar radiation. Think of it as sand grains hiding droplets of water from an unforgiving desert sun. Then there's the matter of temperature fluctuations. While daytime temperatures in sunlit craters are extreme, the nights are equally dramatic, plummeting to minus 280 degrees Fahrenheit. These massive swings in temperature create a dynamic environment where water could continually shift between states, freezing, sublimating, and reforming. This delicate cycle, though harsh, might actually help preserve traces of water by limiting its total loss to space. The interplay of these factors makes sunlit craters an unexpected oasis on the moon. They challenge our understanding of where water can exist and raise intriguing questions about the moon's potential to support life and exploration. What other surprises might these seemingly barren landscapes hold? In the next section, we'll explore the possibilities this discovery opens for future missions, and why these oases might be our ticket to exploring deeper into the cosmos. This discovery might make the moon humanity's ultimate gas station in space. Think about it. Water is the foundation of life, a critical resource for survival and, surprisingly, a key to unlocking the vast reaches of our solar system. Finding it in sunlit craters changes everything. It's not just a scientific breakthrough, it's a symbol of hope, a stepping stone toward a future where humanity thrives beyond Earth. Consider the logistics of colonizing the moon. Previously, the idea of transporting enough water for long-term missions seemed daunting, if not impossible. Every drop of water brought from Earth comes with a hefty price tag, about $50,000 per liter. Now, with water present in sunlit regions, future astronauts could have a local supply. This water could be purified for drinking, used for farming, or even split into hydrogen and oxygen to produce breathable air and rocket fuel. Imagine a lunar base where explorers tap into reservoirs of water just beneath their feet, drastically reducing our dependence on Earth for resupply missions. But the implications go far beyond the moon itself. These sunlit craters could be the launch pad for humanity's journey to Mars and beyond. If we can establish a sustainable way to extract and use lunar water, the moon could serve as a refueling station in space. Rockets departing from the moon, rather than Earth, would need far less fuel due to the moon's lower gravity. This would make long-distance missions more efficient, and open the door to deeper space exploration. Emotionally, the idea of finding water in these unlikely places resonates with something deeply human, the drive to persevere and adapt. Water has always been a symbol of hope, a source of life in the most barren of environments. From ancient desert civilizations to modern space explorers, finding water has always meant survival and possibility. Now, as we stand on the brink of becoming a multiplanetary species, the discovery of lunar water in sunlit craters feels like a message. The universe is full of challenges, but it's also full of solutions waiting to be uncovered. What other resources might we find as we continue our exploration? How far could these reservoirs of water take us, both physically and as a species? In the next section, we'll delve into the technology and innovation required to harvest this water, and the challenges we'll need to overcome to turn this dream into reality. Think about this. A flying telescope helped uncover water over 238,000 miles away on the moon. It sounds like science fiction, doesn't it? But it's very real, and it's thanks to cutting-edge technology and years of scientific determination that we now know water exists in the moon's sunlit craters. Let's take a closer look at the incredible journey from hypothesis to discovery. It all began with a bold question. Could water exist in places on the moon exposed to sunlight? For years, scientists believed this was impossible. The extreme conditions, blazing heat during the day and freezing cold at night, seemed to rule out any chance of water surviving. But new tools and techniques allowed researchers to challenge this assumption, and one of the most groundbreaking was NASA's SOFIA observatory. SOFIA, or the Stratospheric Observatory for Infrared Astronomy, is unlike any other telescope. Mounted on a modified Boeing 747, it soars above 99% of Earth's atmosphere, where it has a crystal-clear view of space. By detecting infrared light, SOFIA can analyze the unique signatures of molecules. When its instruments were trained on the moon's surface, they picked up the unmistakable signal of water molecules, H2O, in sunlit regions like Clavius Crater. This was the first definitive proof of water in areas previously thought too hostile for it to exist. But how does infrared spectroscopy work? Imagine a prism breaking white light into a rainbow of colors. Similarly, SOFIA's instruments separate light from the moon into its individual wavelengths, creating a molecular fingerprint. Each molecule absorbs and reflects light in its own unique way, and water molecules leave a clear and recognizable signature. This technology allowed scientists to distinguish between water and other similar molecules, like hydroxyl, OH, providing a breakthrough confirmation of water's presence. Other missions also played a vital role in this discovery. Data from previous lunar missions, such as India's Chandrayaan-1, had hinted at water on the moon, but these findings couldn't differentiate between water and hydroxyl. SOFIA filled in the missing pieces, combining its advanced observational tools with years of groundwork laid by earlier missions. This journey from hypothesis to discovery is a testament to human ingenuity. It shows how bold questions combined with relentless technological innovation can transform the impossible into reality. As we prepare to discuss how we might extract and use this lunar water, take a moment to appreciate the staggering achievement of spotting water molecules across 250,000 miles of space. This discovery isn't just a scientific milestone, it's a giant leap toward our future in the stars. Could the sun, the very force of heat and light that seems to strip the moon of all moisture, actually be responsible for creating water there? It sounds paradoxical, like a celestial tug-of-war where dry, arid conditions are constantly battling the forces that bring water into existence. Yet this is one of the fascinating mysteries of moon water. Where does it come from, and how does it persist in such an unforgiving environment? One theory suggests that the water is ancient, a relic from billions of years ago. During the moon's early history, it endured a period of intense bombardment by asteroids and comets, cosmic wanderers rich in water ice. These collisions could have deposited water on the lunar surface, some of which became trapped beneath layers of regolith, preserved through the eons in the moon's frigid shadows and perhaps even its sunlit craters. If this theory is correct, the water we've found is like a time capsule, offering a glimpse into the solar system's distant past. But what if the water isn't ancient? Another tantalizing possibility is that the moon's water is being replenished, thanks to interactions with the sun itself. The solar wind, a constant stream of charged particles emanating from the sun, contains hydrogen ions. When these ions collide with oxygen locked in the moon's soil, they can form hydroxyl, OH. Through subsequent processes, this hydroxyl can combine to create water molecules. It's as if the sun, despite its searing heat and radiation, is quietly seeding the moon with water in a delicate chemical dance. Yet another theory involves micrometeorite impacts. These tiny space rocks strike the moon's surface regularly, generating enough heat and pressure to drive chemical reactions that produce water. Over time, these microscopic contributions could accumulate, forming the reservoirs we've now detected. Each of these theories highlights the dynamic, almost poetic balance between destruction and creation on the moon. Ancient cosmic impacts, solar radiation, and even tiny meteorites, all working together to form and sustain water in the most unlikely of places. Is the water we see today a remnant of the moon's distant past, or is it part of an ongoing celestial cycle? The answer could reshape our understanding of not only the moon, but also how water might exist on other seemingly barren worlds. In the next section, we'll explore the challenges and opportunities of tapping into these water sources. But as we uncover the origins of lunar water, one thing is clear: the moon, so often seen as lifeless and static, is more dynamic and mysterious than we ever imagined. Think the moon's water is just lying around in puddles? Think again. The water in sunlit craters is no simple reservoir. It's a marvel of survival, defying extreme temperatures and relentless solar radiation. Much like extremophiles on Earth, organisms that thrive in boiling volcanic springs or frozen tundras, these water molecules endure conditions that seem utterly uninhabitable. But how do they manage it? The secret lies in the moon's fine dusty soil known as regolith. These microscopic grains aren't just passive dirt, they're natural protectors. Water molecules on the moon aren't free-floating, instead they cling tightly to the surfaces of regolith grains. This adsorption creates a kind of shield, with the grains providing a barrier against the sun's radiation. Think of it as water hiding in the nooks and crannies of a microscopic fortress, avoiding direct exposure to the harsh lunar environment. Temperature is another challenge. In the sunlit regions of the moon, daytime temperatures can reach a scorching 260 degrees Fahrenheit, hot enough to bake most materials. Yet at night, those same areas plummet to a bone-chilling -280 degrees Fahrenheit. This constant cycle of heating and cooling could, in theory, cause water to evaporate or sublimate into space. However, the binding strength between water molecules and the regolith may be enough to prevent this, allowing the water to stay locked in place even as the environment shifts dramatically. Interestingly, the moon isn't the only celestial body where water defies the odds. Mercury, a planet even closer to the sun, harbors water ice in its permanently shadowed craters. Though its conditions are even more extreme, the survival mechanisms are similar. Shadowed regions and protective material layers help preserve water. The parallels between Mercury and the moon suggest that such survival strategies might be common throughout the solar system, hinting at a universe where water finds a way to persist even in the harshest conditions. The survival of lunar water also raises broader questions about the resilience of resources in space. If water can withstand the moon's harsh conditions, could similar processes be at work on asteroids or other moons? The implications are profound, not just for our understanding of these environments but for how we might utilize them in future exploration. In our final section, we'll tackle the next frontier, the technology and strategies needed to extract and use this remarkable water. But for now, reflect on this. The moon's water isn't just a discovery, it's a testament to nature's ability to adapt and endure in even the most extreme settings. What if the key to finding life elsewhere lies in the moon's craters? This discovery of water in sunlit regions of the moon isn't just a lunar breakthrough, it's a paradigm shift that echoes far beyond our corner of the solar system. It challenges our assumptions about where water can exist, and forces us to rethink the possibilities for life and habitability across the cosmos. For decades, the search for life has been guided by the concept of the habitable zone, the region around a star where conditions are just right for liquid water to exist on a planet's surface. But what if this definition is too narrow? The moon's sunlit water shows us that even in environments exposed to extreme temperatures and radiation, water can survive under the right conditions. If these molecules can endure such harsh realities, where else might water, and potentially life, be hiding? Take Mars, for example. Its surface is a desert of red dust, battered by solar winds and stripped of a protective atmosphere. Yet, we've found signs of subsurface ice and fleeting water flows. Could the processes preserving water on the moon, adsorption in soil or chemical interactions with solar wind, also be at work on Mars? And what about Europa, Enceladus, or even exoplanets orbiting distant stars? The discovery of moon water broadens the horizons for planetary science, revealing that water might persist in places we once thought impossible. This has profound implications for the search for life. Water is the cornerstone of biology as we know it, and its presence is often considered a prerequisite for life. If it can exist on the moon where conditions are so unrelentingly hostile, it raises the tantalizing possibility that life, too, might be far more resilient and adaptable than we've imagined. It challenges us to expand our search to the unlikeliest of places, craters, asteroids, and worlds far beyond the habitable zone. As we gaze deeper into the universe, the moon's water serves as a reminder. The cosmos is full of surprises. Every discovery forces us to confront our assumptions and expand our understanding of what is possible. If water can survive in the most sun-drenched craters, what else are we missing? What mysteries are waiting to be uncovered in the shadows and light of other worlds? And so, the journey continues. The moon's sunlit craters are just the beginning, a stepping stone to uncovering the secrets of the universe. As we prepare to explore further, let's carry forward the lesson of lunar water, that in the vastness of space resilience and possibility often go hand in hand.